So how do we predict what the shape of a molecule is? The theory that we're going to use for this is called valence shell electron pair repulsion theory. It's a mouthful. So valence shell, and this is an acronym, VSEPR. We usually pronounce this VSEPR, even though that's mixing it up a little bit, but that's better than VSEPR or valence shell electron pair repulsion theory. We'll just call it VSEPR theory. This is based on the idea that electron groups repel each other. So valence shell, so these are the valence electrons, electron pairs repelling each other. And this is the basic idea that helps us to predict shapes. It's a simple model, and it works pretty well. So the name of it has electron pair in it, but what we're going to be talking about is electron groups, okay? So it's very important to understand what is an electron group. An electron group can be a lone pair of electrons. It could be a single bond, a double bond, a triple bond, or a single electron. A double bond has two pairs of electrons in it, but those two pairs of electrons are between the same two atoms and they can't get away from each other, right? They are together, and so we consider them to be one group. Another way you can think about this is you can count electron groups as lone pairs, single electrons, or atoms bonded to the atom that you're looking at. But I'm going to go with this definition. So here we have an example. Here's a central atom, and it's got three different atoms bonded to it. We see this pair of electron. That would be a single bond and a single bond and a single bond. The idea here is that these electron groups are going to repel each other. And they're going to spread out around that central atom to have as much space as they can. So we're looking at maximum separation of electron groups. That's going to give us the minimum energy. That's going to be the most stable configuration, the most stable geometry. So let's look at beryllium chloride. So if we look at the Lewis structure, and all of this is based on Lewis structures, so we need to understand Lewis structures. The Lewis structure for beryllium chloride is going to look like this. Beryllium is one of those things that can have fewer than 8 electrons and still be okay. So we're going to look at the central atom here, bless you, and ask ourselves how many electron groups are around that central atom. Well, this single bond is one group, and this single bond is one group. So we have two groups, and you can think of this central atom as well, it is a sphere. I think of it like being the Earth, and this is you, and this is your X, right? And it was very, very bad. So you hate this person. So here you are, and here's your X. You want to be on the opposite side of the world. I mean, it was bad, right? So as far away as possible, these electron groups are repelled, okay? So two groups getting away from each other are going to be on opposite sides. That make sense? So we can talk about the angle between these electron groups. It's a horizontal line, right? So the angle here is 180 degrees. That's the maximum separation. So we call this a linear geometry because these three atoms are in a line, right? We're not trying to be tricky here with these names. Linear geometry in a line. So VSEPR theory predicts this, and experimental observation confirms this. This is the shape that beryllium chloride takes. Let's look at carbon dioxide. Draw the Lewis structure. Oops. So looking at the Lewis structure for carbon dioxide, you see something like this. So we're going to look at the central atom, and we're going to see how many electron groups are attached to that central atom. Not 4, 2. It's not pairs. Yeah, it's hard to get straight. It's not pairs. It's electron groups. And this double bond is one group, because the electrons in this double bond have to stay between the carbon and the oxygen. They can't get away from each other, right? They're attached. So that's one group, and here's another group. So 2 groups. Again, 2 groups get away by going on opposite sides. And so we'll also have a linear geometry for carbon dioxide. Bond angle of 180 degrees. 2 groups. Let's look at 3 groups. So boron trifluoride. Might draw the Lewis structure like this. We tend to do right angles for Lewis structures. And this was one of the examples we used in incomplete octets as exceptions. So you look at the central atom. How many electron groups? 3. 1 for each bond, right? A single bond, a double bond, a triple bond, each of those is just one group. If that is just not working with your brain, you can look at that instead by saying, well, how many atoms are bonded to it? 3. Are there any lone pairs on the central atom? No. So there's 3 groups. How do 3 things get away from each other? Well, they're going to form a triangle in a plane, right? You can't have 180 because then this person is going to be too close to these guys, and this is 3 people that hate each other. Right? We went from talking about everybody being happy to now everybody hating each other and trying to get away. So 3 things getting maximum space. So 120 degrees. This is a triangle, and it's flat. It's in a plane, and so we call this trigonal planar geometry. Because my exams are mostly multiple choice, you don't actually have to remember exactly that name, trigonal planar. You just have to be able to recognize it as one of the multiple choice answers, right? So if you're thinking flat triangle, as long as you can recognize that that's what that means, then you're okay. Formaldehyde also has this geometry. If we look at formaldehyde, it's got this Lewis structure. How many electron groups on that central atom? 3. If you prefer to count atoms, there's 1, 2, 3 atoms. If you can prefer to count bonds, a single bond, a double bond is 1 group. There's another single bond, 3 bonds. No lone pairs. So 3 bonds get away from each other, spreading out in a triangle. What's different here, though, is that these things are not all the same. The oxygen is bigger than the hydrogens, and the oxygen has a double bond, and these guys have single bonds. The oxygen bond is more repulsive, or you can think of it as just taking up more space. And so it's going to push these 2 guys a little closer together, and this angle is going to be a little more than 120. This one will be a little less than 120. So when there are different types of groups, they're going to affect the exact angles. I don't expect you to remember these particular angles. The most I would expect you to say is that this is greater than 120, and this one is less than 120, because this double bond takes up more space, and so it's going to push the other 2 together a little bit. Any questions? Molecules with 4 groups, now we're coming out of 2 dimensions into 3 dimensions. And so I like this balloon analogy. Each electron group is like a balloon tied at a central point. And those balloons will spread out in just the same way as these electron groups because they're trying to get some space. So 2 balloons tied together will make this shape. You tie a third balloon in there, it's going to push these 2 over, and they're going to be equally spaced, right? Here the balloons are representing electron groups, and so we have to remember that lone pairs are electron groups. If we have 4, the 4th balloon on that flat triangle is now going to push the triangle down a little bit. And it's going to have a 109.5 degree angle here, not a 90 degree angle. Because it can use 3-dimensional space, and so it's going to. So if you get 4 things separated around a sphere, you get bond angles of 109.5. We describe this shape as a tetrahedron. A tetrahedron is a shape that has 4 points. 3-dimensional, regular, solid. That's what they call it, yeah, with 4 points. Tetra means 4. How many points does a triangle have? 3. Tri means 3. So this is tetrahedral. 4 identical faces, 4 points. So each of these faces is a triangle. And this is definitely harder to see. We've got the triangle here. And then this triangle is this one over here, and then there's one on the back, and there's one on the bottom. So methane, we've talked about a little bit. CH4, there's its Lewis structure. It's got 4 groups. They're all single bonds. And those 4 single bonds will arrange in a tetrahedral shape. When we draw the Lewis structure, it looks flat, right? This angle would be what? 90 degrees. But the molecule isn't limited to 2 dimensions. So when it goes into 3 dimensions, takes up 3-dimensional space, then the angles can be larger, 109.5. They're trying to get away from each other because they repel each other. And so larger angles is going to be more stable. So what happens if you have 5 groups? So the 5 groups are going to make a shape that we call a trigonal bipyramid because it's 2 triangular pyramids. So bipyramid, and the base of the pyramids are triangles. So this is what the balloons look like. And we've got 1 balloon on the bottom and 1 on the top, and there's 180 degrees between those 2. But in the middle here, we have these 3. We can also look at it as a ball and stick model. So we've got straight up, straight down, and then we've got 3 in the middle that are spread out evenly. So if this is the North Pole and that's the South Pole, these chlorine atoms are along the equator, right? So we call this an axial position, and this is an axial position, and these are equatorial because they're going around the middle. The angles here are not all the same. The angle between an axial and an equatorial position is 90 degrees, but the angle between 2 equatorial positions is 120 degrees. There's no way to spread these things out where they can all be evenly spaced from each other. This doesn't work. Let's add a 6th group. So that 6th group is going to squeeze into the equatorial position here. And now what we have is an octahedron. So an octahedron, and all of the angles between any 2 adjacent groups are going to be 90 degrees. So we still can think of axial and equatorial, But it's not very significant here because all of the angles are the same. They're all 90 degrees. So we should be able to do something like this. Determine the molecular geometry of carbon tetrachloride. You have to start with the Lewis structure. So carbon tetrachloride, we'll put the carbon in the middle and put the chlorines around it. And then we have to consider the total number of valence electrons. And I'm going to just fast forward through all of that. Oops. So there's the Lewis structure for carbon tetrachloride. Start with the Lewis structure, and you look at the central atom and you ask yourself, how many electron groups? 4, right? There are 4 single bonds, 4 electron groups. How did 4 balloons get away from each other? Tetrahedron, right? So we've got 4 groups. That means we've got a tetrahedron. Or tetrahedral geometry. When we draw the Lewis structure, it looks flat. It's not flat. You got the chlorine in the middle. I'm sorry, the carbon in the middle. The carbon in the middle, and you've got a carbon up there, and you've got another carbon over here, and then this one is kind of coming out at you, and this one is sort of behind. We can also draw that with the letters, and we can use wedges. The wedges are coming out at you, and the dashed line is going behind the screen. Any questions? 4 groups, tetrahedral.